back to Backbenchers Academy by Rohit Verma, and here we are back with our next video based on the topic TIR is in prisms. So total internal reflection in prisms, wherein as per the particular scope of syllabus, we're supposed to be concerned with these three types of prisms. First of all, the prisms are categorized into the three categories, namely, first one is isosceles right angled prism with the configuration 90°, 45° and 45°. Since it's an isosceles prism, which means two angles are equal or two sides are equal, so both the other angles are 45, 45 and one is 90, being a right angle. So this is how it looks like, a triangle with vertex B as 90° and the other two angles being 45 each. Second is equilateral prism. Equilateral, all angles are equal, 60, 60, 60. That's the configuration of the triangle, which is the area of cross section, triangular area of cross section of the prism, with all the three angles being equal to 60° each. And the third type of triangle is the right angled prism. The third type of prism is the right angled prism with one angle 90, other is 30 and 60. So this right angled prism is different from the isosceles right angled prism because here there were two angles equal. The other two angles other than 90 were equal to 45, 45. Here is 30 and 60. So that's how it looks like. So today in our discussion, we're going to talk about these three types of prism, and we will understand how total internal reflection takes place in these respective three prisms and how is it implemented practically. Alright everyone, so now let's understand the first category of the prism that we need to discuss, which is isosceles right angle prism, in which the total internal reflection can be used for these three phenomena. There are three subtopics, there are three certain ways in which TIR can actually help us in this kind of a prism, which is isosceles right angle prism. The first way is TIR can be used in such a prism to deviate a ray. Deviate means to shift its path, to deviate a ray of light via, that is through 90 degrees. So we can shift the ray through 90 degrees. If it's coming like this, we can bend it off either like below or above. It's both 90, this or that. We can bend it through 90 degrees. We'll understand how. Second is it can also be used to deviate a ray of light through 180 degrees. And the third way is we can erect an inverted image. So if there's an inverted image which is like this, upside down, we can actually erect it, we can create it straight using a right angle prism, isosceles right angle prism, and without any deviation. So what we can do is we can erect an inverted image without any deviation using isosceles right angle prism with the help of the phenomena of TIR. So let's understand them one by one with our very first particular deviation of a ray of light through 90 degree. Alright everyone, so let's understand how we can use TIR in an isosceles right angled prism to deviate a ray through 90 degree. So if you see here in the diagram, we've got ABC, which is an isosceles right angled prism, the triangular area of cross section of the prism, with angle B is 90 degree. The other two angles are 45 each. And we've got PQ. What exactly is this PQ? This is the object. And we're going to pass through two rays out of this, which will come perpendicular to the surface. Let's start the process through. So from this PQ, where P is the top portion of this particular object and Q is the bottom portion, there are two rays that come perpendicular to the surface this way. Though there are infinite rays which actually comes out of an object, we're just using ideally two rays to keep our process simplified and easy to understand. So these two rays, since are coming here perpendicular, so the value of I1 for both of them is 0 degrees. What exactly is I1? I1 is the first angle of incidence, because this is the first time that our particular ray is touching the surface of the prism. Since angle I1 is 0, it means there will not be any deviation possible here, and the ray will pass undeviated. It passes straight away over here. I'm showing you the process first from one of the rays. The second ray will follow the same thing in the same way, and this phenomena will be repeated twice. So it comes up straight. This angle is also 90 according to linear pair. Now if you see this particular triangle, I'm just naming this point, let's suppose, as R. So in this triangle A, this is suppose SASR. In triangle ASR, one angle is 90, second is 45, third automatically becomes 45. So this angle is 45, and since we've touched another surface over here, Now, whenever we touch the surface of a prism through a ray, we need to first draw the normal so as to find out and figure out what is the value of the angle of incidence at this point of intersection if we can find. So let's draw the normal. I'm just shifting this R a little at the bottom, and over here let us draw this being the normal. Now if this is normal, that means this angle is 90 and the above angle is 45, so the remaining angle also becomes 45. This is our second angle of incidence, which is, if you pay attention please, this is in the denser medium because we are right now inside the glass. The ray is inside the glass. Glass is denser, as we can see. And the value of critical angle for glass, as we have studied already, is 42 degrees. And the angle of incidence being formed here is 45 degree, which is greater than the critical angle. So this is the third condition of the critical angle. If you've not studied this topic, you can see one of my previous videos based on the same, which is by the topic of critical angle and total internal reflection, so as to understand this better. So being the third condition, now it will actually suffer TIR, which means this ray will actually be reflected with the same angle, because as per the law of reflection, angle of incidence equals angle of reflection. So this is also 45 degrees. And this ray touches over here, wherein if this is 45, this is 45, this is 45, the remaining is also 45, since the total angle on the straight line itself is 180, which is split in 4 parts, equal parts, 45 each. Now in this triangle, 45 and 45, two angles of 45. So according to, again, angle sum property, this angle turns out to be 90, which means at this point the angle of incidence, which is I3, turns out to be 0 degrees, due to which now the ray is again gonna pass undeviated, which is straight. It will come outside straight away. And since we had two particular rays, so let me just show you what happens to the other ray. As I told you earlier, that I'll show you with one ray, same phenomena will be repeated with the second one. So let's repeat that phenomena. Here is 90, it goes straight, angle of incidence is 0. The 90 as well, 90, 45, this is 45 by angle sum property. Again a normal here, this is again 45. This is also the second angle of incidence. You don't need to mention it, it's pretty much understood. And then here suffers again TIR, it drops down. The arrows are important because there are deductions for not making the arrows. So please be very careful. A diagram in science must be labeled, because an unlabeled diagram is basically going to be like incomplete, so you lose marks onto that. So this again is 45, drops down here. This is going to be 90 as well. Same way this comes out. Now the question comes up, what way will we draw the projection of this object PQ which we've taken here? If we see here, it goes this way up, bends this way, it bends this way, goes down, comes here. So if I take this particular tip, if I consider, let's suppose, the tip of this chalk to be the head of this object PQ, like this. It goes straight first, then it bends, drops down, comes over here. That means this head comes this way, that's why this becomes the projection of the object PQ, where this is labeled as P dash and that's Q dash. Now, the thing to understand over here is that what we were supposed to do, we were supposed to deviate a ray by 90 degrees. Have we done it? Of course, we have. How? See, this was the incident ray, this is the emergent ray. That is the angle of incidence, the angle of deviation, sorry. That's the total angle by which the ray is deviated, which is nothing but 45 plus 45. That means the total deviation angle is equal to twice 45, which is 90 degrees. And you can very clearly see that's how the object is. If I explain you in another way, this was the object PQ. This is the image P dash Q dash. So if you observe, they are at a particular difference of the deviation angle being 90 degrees. Now the question comes up, where is it used? Let's understand. What is happening here? Reflection. Is it complete reflection with total 100% energy conversion? Of course, yes, because the energy is not getting lost here. Since this is TIR, total internal reflection, with no losses, it means that whatever amount of light was coming from here is coming over here as well. This is used in a periscope. It's a very good 2-mark question that can be used here, can be put forward. Why exactly can we use a prism instead of a mirror in a periscope, because we studied in previous classes and smaller classes that in a periscope, which is a device often used in submarines and other particular appliances, or you can say in other machineries, in ships, that in a periscope we generally use like two particular mirrors kept at a 45-degree angle. When you talk about mirrors, there's one thing associated with them. Every time they reflect light, they absorb light as well. That's exactly why if you actually are going to a gym, let's suppose, or at any place where there are mirrors in the front and the back as well, like in a dance class, in a Zumba class, in particularly a barber shop or anywhere of this kind of place, then there are two particular mirrors, one in front of you, one at the back. So you have multiple images, infinite images, and every time you see the next image, the image becomes dull. The amount of clarity or the resolution of this image drops down, because every time the mirror is reflecting, it is absorbing some amount of energy with it. But that is not the case with a particular prism. So that is why prisms do replace the mirrors. So it's a very good question which often is asked, that why is it beneficial? Why is it actually an advantage to use a prism instead of a mirror in a periscope? That is because it has 100% energy transmission and there is no loss of energy. That's it for Alright, so that was the deviation by 90 degree, and now let us understand how can we use the same prism, that is an isosceles right angle prism, the same phenomena which is total internal reflection, but creating a deviation of 180 degrees. So see, we're using the same thing and we're using the same phenomena, but the only thing is our perspective is changing. The way we were using that prism is changing because it has three surfaces. So now we have rotated the entire particular prism in such a way that the base becomes the hypotenuse. The hypotenuse is the base now, and the right angle is now right on top. Earlier, as you remember, the diagram was like this. So the prism was kept with the base being not the hypotenuse. This was how it was kept. The ray came like this, passed on this way. Now we have shifted it, how we have rotated it basically. So it's just the perspective being changed. So you can say it is just a slight modification to our experiment that we're doing, in such a way that this is ABC is the triangular cross section of the prism that we're taking, which is the isosceles right angle prism with two angles 45 and one being 90 on top. PQ is our object, wherein we're going to use two rays this way as well, which are coming perpendicular to the surface, this way and this way. Now the same way of becoming perpendicular, which means that the first value of I, which is I1, is 0 degrees, and that means there is no deviation. They pass undeviated. Now, this time as well, I'm going to show you the processes with one of the rays. Second ray follows the same process. So let's say take this ray. It moves straight away, this till here. This is 90, so vertically opposite angle. This is also 90, 45, 90, which means this is also 45. And now we've touched the other surface of this prism, which is AB. So we create a normal so as to get to know where is or what is the value of our next angle of incidence. So this is our normal, wherein this angle, which is 45 degree, is the angle of our second incidence, I2. The second angle of incidence is 45 here as well, which is greater than the critical angle of glass, which is 42 degrees. So 42 degrees is the critical angle. So this is 45, coming up to the third case of TIR. So TIR happens here with the same 45 degrees, and this is also 45. So here also the same phenomena happened, that 180 degree angle was split up into four particular segments or four particular parts which are equal parts, 45 each. The same phenomena is repeated with the second ray. This was the normal. This is our 45 degree, which is our I2, and this is 90, bends here as well, passes straight, touches the medium here, doesn't go out, it touches. Now this is 45, 90, so this is also 45. Since we've touched another surface of the prism now, which is BC, we create another normal, wherein this is 45 as well, and this is again greater than critical angle, so it bends further at 45 degree, which is 90 degree bending because it's coming 45 twice. So here also it bends again. This 45 I'm writing separately over here so that it doesn't come on its way. So this is further on 45 and 45 as well. Which means that so far in the process, the total internal reflection phenomena has happened twice. Once over here and once over here. Once on the surface AB, once onto the surface BC. Wherein at this particular point of intersection, this was 45, since again 180 degrees separated into 4 particular equal angles, 45 each. This is also 45, so this is 90. So that means now for the third time, I3, the third time we've touched this particular surface of the prism is 0, because the surface is perpendicular to the ray, or you can say the ray is actually perpendicular to the surface, so it passes out undeviated. It comes out, emerges out. Now let's understand, important to know whether this projection of PQ will come this way or this way. Let's understand. This was PQ. Let's suppose I assume this particular chalk end to be the pointed part of the object. P goes straight, bends, becomes straight, bends again, goes down. P is pointed to the right, which is this is the right one. So we remove this. That means this is the projection of our image, which we are labeling as P dash and Q dash. Now if you observe over here, if you just observe, PQ, which is our object, was this way. This was PQ. And this is P dash Q dash. And if you carefully observe the angle between the two of them, it's 180 degrees. Why? Because 90 bending was done here. It was bent by 90 degree angle over here, and 90 was bent here. It's twice 90. It obviously becomes total deviation angle turns out to be 180 degree over here. Then total is 180 degrees. So which means that now further we have used total internal reflection in an isosceles right angle prism by keeping the base to be the hypotenuse, and we have deviated the ray via or through an angle of 180 degrees. Coming up to its particular application, the application of this particular type is in binoculars and in cameras. So in binoculars and in cameras, we use this particular phenomena of the TIR in an isosceles right angle prism. You must know the uses, you must know the labeled diagram of how to complete this particular process, and you must know what deviation are we creating, 180 degree deviation we are creating, because in a question, the question can be framed on any of these three perspectives which I have emphasized here in the video, which is topic, the deviation angle, that is the use, the two uses, and the diagram, which is should be a labeled diagram. Arrows are pretty important, the angles specified are pretty important. So here we are with our third subcategory of the prism that we were talking about, which is an isosceles right angle prism. As you can see, one angle 90, two angle 45. There's a third particular subtopic in which what we're going to do is we'll see how can we use an isosceles right angle prism, and we can actually implement the phenomena of TIR so as to erect an inverted image without any deviation. So now what exactly is special about this particular subtopic is that there is the way we are putting this ray incident is very much different. In the previous two conditions, when the ray was coming and it strike to the prism for the very first time, the angle of incidence was 0. It was coming perpendicular. This time it's not really so. Let's see how. So this is ABC is our isosceles right angled prism, which is the triangular cross section of the isosceles right angled prism. PQ is the image which is inverted. As you can see, we're going to create its projection which will be erect. So P is the head, which is towards the down arrow. Q is the tail, which is on top, which is actually the opposite of erect, which generally it is. So it's inverted. We're going to see how we're going to create it into erect one. So as usual, we're going to use two rays. I will show you the process by one. Second one will follow the same process. There are some details about this particular topic which are different from the previous two conditions that I'm going to emphasize, and you must take care of those. So first let's take out one ray this way and the other from Q, coming horizontally straight onto the surface AB. Now something to note here is that if you observe, being the normal, this angle of incidence is not 0 here. I1, what I mean is I1 in this condition is not equal to 0. That's exactly what we have to write. Or we can simply write I1 or we can write I1 not equal to 0. We don't really know whether this is 1 degree or 2 degree or 7 or 27 or whatsoever. We're not concerned about the value, because for concerning about the value we need to actually perform this experiment in practical, which is not really required. What you need to do is, as a student, and for the exam point of view, you must know that I1 just has to be mentioned as not equal to 0. Now, being, the process being a transmission from air to glass, because we're coming from air to glass, that means we're going from rarer to a denser medium. As we've studied, we're going to actually bend this ray up towards the normal, because we have less space inside. So what will happen here is, being the normal, it would have gone straight, it will bend towards the normal way and down this way. By how much angle we're not concerned. I'm just removing this air and glass. This was just to explain it to you, so as to create space over here. So the same way, this will be a normal and it will also bend over here. Now for the second time, now this was the first, this is the second time. Now the ray will actually touch this particular glass surface, wherein this is the normal. Now, what I'm telling you right now at this point of time, the angle of incidence, which is the second angle of incidence I2, it will always be greater than the critical angle C. This is a conclusion which is based on the practical implementation of the same, or you can say as per the experimental results that we've concluded through. So we just need to write here that I2 is greater than C. It's more than critical angle, which means we are on the third condition of critical angle, and this shows TIR. Total internal reflection will happen, wherein these two angles will be equal. This also will be equal to I2 only, whatever is the value. Now, as we know that the critical angle of glass is 42 degrees, so this angle is surely greater than 42. Whether it's 42.5 or 43 or 47 or 48, we are not concerned about it. As I told you, you need not worry about it, and you don't even need to write this thing that this is greater than a critical angle. So the value can be anything. It's based on experimental confusions. This need not be written. It's not required. You just need to simply write this. And now at this point, third point, when we touch the medium, we are going out in the rarer medium. So obviously it will scatter away from the normal, and as per the particular conclusions based on experimentation, this is how the ray will come out. It will bend away from the normal, not towards, but away from the normal, in such a way that these two rays will be parallel. This is not a very accurate diagram, since I'm not really using a scale and a pencil. So this is just an approximate diagram. They will come in symmetry. They have to be in a symmetry. They will literally come in a symmetry, wherein the point to be understood here is that at this particular point of time, this I3 over here has to be written. This is just that less than the critical angle. The critical angle is more in this case, which means that in the third condition, when we touched the glass surface, the angle of incidence, that is I3, was less than the critical angle. That is why we suffered refraction of light and the light came out of the surface. Now, the question comes up whether the projection of this image will be actually erect. Let's understand. I'm assuming this particular image to be the inverted one, where this particular chalk part represents the pointed part, the arrow part. Goes straight, bends, goes down, bends again, then it further bends, goes up, goes straight, and that's how it is. So the tip is on top. So this is basically the projection, which is, this is P and that's Q. So if you observe over here, as we can clearly see, this is inverted, wherein this one is erect. So we have actually reached up to our conclusion, which is we have created an erect image out of an inverted one without any deviation. There's no deviation in this condition, as we observe, and this phenomena is practically implemented in a slide projector. So these are the three perspectives which you must know about this topic. The purpose of the topic or our agenda. Second is the use. And third is its implementation in the form of the diagram, with the labeled diagram showing all the arrows from the incident path to the emergent path, and showing all the necessary values of the angles, maybe I1, I2, I3, or whatever necessary angles required. Now it's time to discuss our second type of prism, which is an equilateral prism. We've discussed already the three conditions of the previous type of prism, which was the right angled isosceles prism. And now here we are. We don't have any subcategories in this one. There's just one diagram that you need to know, which is, if you see here in front of us, we've got an equilateral prism, which is all angles are 60 degrees. This is ABC being labeled as. And we have an incident ray which is coming perpendicular to the surface. So which is obvious, the first thing, that I1 is surely 0. So the ray will go undeviated. Now there are two particular possibilities. Either you can let the ray pass from let it be incident on the surface AB from the top or somewhere from the bottom. It will be the same way up. We just gonna follow the same process. There will be TIR or total internal reflection that will happen once, and then the ray will emerge out of this prism. Let's understand how this goes on in the way I have shown here in this diagram. So the ray comes straight away, goes inside and touches the front surface onto the right side, which is BC on this point. Now this is 90, this is obviously is 90, this has passed up and deviated. Being 90 and 60, as per angles on property, we can figure out this is 30 degree. Now since we have touched the prism on another surface now here, which is BC, we draw a normal so as to figure out our angle of incidence, which comes out as 60 degree, which is obviously greater than the critical angle, since our critical angle value is 42 degrees. So it suffers TIR over here and it bends at an angle margin of 60 degree as well, wherein the other remaining angle turns out to be 30 degree. Now if you see here, after bending, after suffering TIR, which is total internal reflection, at this point, when it bends down and touches the surface again for the third time, this was the first time, second time, and now the third time we are touching the surface of this prism, we have this enclosed triangle, one is 30 degree, one is 60 degree, the third angle will turn out to be 90, which means the value of our I3 is coming as 0 degrees, since it is straight away falling on the normal and it emerges out this way. That's as simple as that. It's pretty easy. This is the diagram that you need to know, that it has to be a labeled one. The angles must be definitely mentioned, and you must of course use a scale and pencil to draw it. That's it. That's all you need to know about this. Alright everyone, so here we are with our third type of prism, the final one, which is the TIR phenomena in a right angled prism. The configuration of this prism is 90, 60 and 30, wherein, as we can see in the diagram, this is ABC being the triangular cross section of the prism, wherein angle A is 90, B is 60 and C is 30, and this is an incident ray falling perpendicularly on the surface AB, which obviously means that the value of I1 turns out to be 0 degrees and it passes undeviated straight away inside. This is very much similar to the previous type, that is the second type of prism. The phenomena will be very similar. So if you see here vertically opposite angles, since these are, so this is 90 as well, this is 60, and this angle turns out to be 30 degree. Now here, since we've touched this prism on another point, we draw a normal over here, and this remaining angle turns out to be 60 degree, which is greater than the critical angle, since critical angle was 42. So we suffer a TIR phenomena over here, such that this angle is 60 as well because of the total internal reflection, and the remaining angle turns out to be 30 degrees. Now this particular ray goes obliquely or slantly onto the other sides and touches this prism on the surface AC. This is 30, this is 30. By angles on property, this angle, since 30 plus 30 makes it 60, and 180 minus 60 makes it to be 120 degrees. But we need to figure out what is our I3, because this was I1 being 0. This 60 was our I2. I forgot to mention here, I'm just doing it, that I2 was 60. Let's talk about I3. But for finding our angle of incidence, we need one thing. That is, yes, you're right, that is the normal. So we draw the normal over here, perpendicular to the surface. And since this is 90, so this angle is 120 minus 90, which is 30 degrees. So that means I3 is equal to 30 degree. So I hope you understood what I've done. I've drawn a normal here, which is perpendicular. So this is 90. This whole thing was 120. I just subtracted 90 out of 120. So I just need to find what is the angle between the normal and the incident ray, which is this angle, which is 30. So I3 is 30, which is less than the critical angle, because critical angle was 42. So now we have basically the phenomena of the refraction of light will pass out of this particular prism, but it will bend as well because we're changing the medium. Since we are in a denser medium and we're going in the rarer medium, and on top of that the angle of incidence is not really zero over here. So ideally this ray would have gone this way if there was no deviation, but we will deviate towards, no, away from the normal. So this ray passes on away from the normal because we have lots of space outside in air, so it will bend outside away from the normal, and this can be referred as E, angle E, where angle E means the angle of emergence. This entire phenomena shows how a ray will actually pass through a prism if we are using a right angled prism with the configuration 90, 60 and 30, and the ray is coming perpendicular to the base. This is the base. That's it. It's easy.